All right, so we have officially begun. So we last time we were talking about the product and the quotient rules, and I still have that. We're not through talking about that, but I still have that due for Saturday evening. This one is lengthy, though. There's lots of problems here because you need lots of practice with the product and quotient rules. And then we haven't discussed higher order derivatives yet, although that won't be conceptually all that difficult at this point to grasp. So we're going to talk about that today. But I still have this due on Saturday. So you want to try to make as much progress as you can because, again, this is lengthy. There's 25 problems here. So that's longer than most of the assignments. So you will need more time to work on this one. And we're also going to talk about another differentiation rule today called the chain rule. And this one's maybe a little bit more conceptually difficult than the product and the quotient rules. And so I just have that assignment due on Tuesday. We'll see if that's really, a good time frame or not. But of course, the thing to be concentrating on right now is this current homework on the product and the quotient rule. Now, I did want to mention one problem that was in the homework that was due yesterday, I think. And so, by the way, so if you didn't work on that homework, and there's a couple of you who didn't either make a high score or you didn't start that one, don't forget, you can still request an automatic extension. So you just need to go to, I think, past assignments and click on past assignments maybe, or yeah, I think maybe past assignments, and find that assignment and open that assignment and then choose automatic extension request. And I don't have to approve that. That just is approved automatically. And then you can continue working on that assignment and getting points. You can work on all the assignments after the due date, but you just don't accumulate any more points, right? But if you ask for the automatic extension, you can accumulate more points, right? So it would be good to have some grade in the grade book. Even if it's not going to be a high score, some grade in the grade book will help your homework average, right? That's better than a 0. So you still have time to request that extension for that last homework, the one that was due yesterday. Okay, now let me mention this problem then. So let me adjust the screen here a little bit so I can write. So there was, this is not the last problem, I don't think, but it's close to the end of that homework. You might have had a slightly different version of this problem. I didn't write the whole problem, but here's what the problem said. They give you this function, f of x is kx cubed. So this is a cubic function, but notice this coefficient here, x is the input variable, but this coefficient they're leaving unspecified, right? They're leaving that as a variable. So this is just some number k. It could be 2, 3, minus 2, minus 3, something, right? Times x cubed. And what they want you to do is find that value of k so that this function will have this tangent line, y equals 5x plus 7. Now, in your version of the problem, the tangent line might have been slightly different, okay? So these coefficients might have been different, but this is the version that I saw. So I noticed that this came up as a flagged problem that lots of people were either having multiple attempts on or weren't able to answer. So, and I don't remember I didn't talk about this problem in the lecture, right? So I thought I would go over it, how to do this one, because this does take a little bit of thought to figure this one out. Okay, so again, we're trying to figure out what's the correct value of k here, so that when you plug that value in for k, this function will turn out to have somewhere the tangent line y equals 5x plus 7. Now that is already a little bit of an ambiguous question because functions will have lots of tangent lines, right, at each value of x. you may have a completely different tangent line. So, so there's really two questions here, not just one. It's not only what is the value for k that will yield this tangent line, but also really what is the value for x? You know, it's what x value on this curve is going to have this tangent line, because different x values on this curve will have different tangent lines. So this is really kind of a complicated question. You're really looking for two things here, not just what is k. That's what they ask you, but really along the way you also have to discover what's the correct x value for this function. Okay. All right. So let me show you how you can think about this one. And so it's clear, since you're dealing with a tangent line, right, for this function, and of course, you know, tangent lines have to do with derivatives, right? So it's pretty obvious you're going to have to compute the derivative of this function. That's going to come into play somehow in the solution of this problem. So let's go ahead and find the derivative of this function f. Even though there's a k here, we can still find the derivative, because remember, k is just a constant. X is the variable in the problem. K is going to be some specific number. We're getting ready to figure out what that is, right? So f prime of x, then, the derivative, right, would be, well, you just use the power rule, right, to differentiate this. You don't have to use the product rule here, because, again, k is not a variable. That is a constant. So so you can just use the power rule, and so you get what? 3, bringing the 3 down, right, times k. The k is just going to stay there as a factor, and then times x squared, right? You subtract 1 from the exponent. So you know the derivative of this function, 3k times x squared, right? Now, of course, the derivative is what gives you, right? The derivative is what gives you slopes of tangent lines, right? If you want to find the slope of a tangent line at a particular x value, you take that x value and you plug that into the derivative, correct? Right? So here's the derivative for computing rates of change, but those also happen to be slopes of tangent lines. And the slope of this tangent line is 5, correct? So we know somewhere for some x value and some k value, right, the derivative, which gives you the slope of the tangent line, that has to turn out to be 5, because the slope of this tangent line is 5, right? So sort of the first step in the, or maybe the second step in the solution of this problem, right, is to take your derivative and set it equal to 5, because that is the slope of the tangent line that you are given, right? So notice now, when you take that derivative and set it to 5, you get an equation, okay? And, you know, we like equations, right, in algebra, because we can solve equations and, you know, find answers that way, right? So, so here's an equation that hopefully at some point we'll be able to solve, so we can figure out what's the value for k, because that's the question that we were asked. However, the problem with this equation, right, is that it's got two variables in it. So it's not just 3 times k is equal to 5. That would be easy to solve. Or it's not just 3 times x squared is equal to 5. That would also be a little bit harder, but still easy to solve. This equation has two variables in it. And you're usually not going to be able to uniquely solve for either of the variables one equation if the equation has two unknowns in it. So what we need is another equation, okay? We've got two unknowns that we're looking for here. Usually when you're dealing with multiple unknowns, like in this problem, you need as many equations as you have unknowns, okay? So we've got two unknowns, but only one equation. So that's unfortunate. So we're going to have to figure out another equation. So that's where we have to sort of rack our brain here, right? So this is kind of the tricky part of the problem. Where are we going to get that other equation from? So what other piece of information are we sort of overlooking here that we can use to help us find an equation? And the answer is, well, we have to remember geometrically, right? The tangent line is going to touch the curve, correct, right? So at the x value where the tangent line is tangent, it's going to touch this curve. So these two curves are going to intersect each other at a point. Now, okay, now that reminds me, back, you know, in the beginning of the class, we talked about how you find the point where two curves intersect each other, right? Remember discussing that? are doing problems like that, that was way back early in the course. How do we figure out where two curves intersect each other? What do you do? Do you recall what to do there? Anybody remember that? So if you're looking for where two curves, so we have two curves here, this curve and this line. If we're looking for where they cross or where they touch each other, where those two curves cross, you set them equal, right, Colin? That's correct, right? That's what we did. So that is where the second equation is going to come from. I'm going to take not the derivative, but the original function, k times x cubed, and I'm going to set that equal to the tangent line formula, which is 5x plus 7. Yay! Now I have two equations, you see, okay, involving these two unknowns, x and k, and now I have a chance to use those two equations to find the values for x and k. Now, that may not be trivial, but at least I have a shot at it. Now, the rest of this is going to involve a little bit of algebra, and if you're not looking at this exactly correct, the algebra here can even be a little bit tricky. So let me show you what you can do, though. But you may have approached it differently. There's other ways of using these two equations to solve for x and k. All right, look here. Notice that this equation, this first equation, we can pretty easily solve this for k because, so in other words, I can get k on one side of the equation by itself by dividing both sides by 3x squared. So I'm going to divide let me actually do that step. So I'm going to divide the left-hand side by, which is 3 times k times x squared. I'm going to divide that by 3x squared, but then I have to do the same thing to the right-hand side, right? So I'll divide the 5 by 3x squared. I'm hoping x isn't 0 because then I'd be dividing by 0, and we're not supposed to do that with equations, but we'll just have to take that chance, you know, because what choice do we have here? So notice what happens is the 3 and the x squareds divide out, right? And so you end up solving the equation for k. You know that k is 5 divided by 3 times x squared. Now, the reason that's helpful is now you can take the 5 divided by the 3 times x squared, and now you can plug that into the second equation where you have k. So where you have k, you can now use 5 over 3x squared, because that's what k is equal to according to the first equation. So we get 5 over 3x squared times x cubed is equal to 5x plus 7. And now this works out so beautifully here. Notice the x squared will divide into the x cubed. So you end up getting 5x, just 5 times x now, because 2 of the x's divide out, over 3 is equal to 5x plus 7. And now you have an equation here with just one unknown in it. And now you know how to solve equations with one unknown, right? Okay, right. So, so this equation is, you've learned how to solve back in beginning algebra. Actually, let's do this. Again, there's multiple ways of going about this. I'm going to multiply both sides by 3 so I can get rid of this 3 out of the denominator because I don't like having fractions there, right? So I'll multiply both sides by 3. Don't forget to multiply both sides. So the 3's will divide out, and so you'll have 5x is equal to, and then 3 times 5x plus 7 is 15x plus 21. That's not too bad. And so now I'm going to rearrange terms. So I'm going to bring the 5x to the right, change the sign, and I'm going to bring the 21 to the left. And don't forget to change the sign. So you get minus 21 is equal to 10x, or it looks like x is equal to minus 21 over 10. So, well, we get a strange value for x there, but, you know, who cares? There it is. X is minus 21 over 10. If I did my arithmetic right there, x is minus 21 over 10. And now you can figure out what k is from this equation, right? Okay, so you get k is equal to 5 over 3 times x squared, but x is minus 21 over 10. So where you have the x, you can plug in minus 21 over 10. And then don't forget you have to square that. So you're going to get a strange value for k here. I'm not going to simplify this, but you get a strange value for k, but and there it is, okay? Once you, once you simplify the arithmetic here, there's how you find the value for k. So it's going to be some unusual fraction, but anyway, there it is, okay? So there's how you solve that. That involves solving these two equations for these two unknowns, k and x. So that's kind of that's a little bit more advanced sort of question. Okay. All right. So if you were struggling with that one, well, there's how it's done. All right. So are there other questions there quickly from the homework? We did a couple of them last time. So we've done some of the things on the homework. Anything else that people want to ask me about quickly from that one? This is from the prior one that we just turned in. Okay. All right. So I'll take your word for it. Everyone is I'll take your word for it. Everyone is comfortable with that assignment. Basic differentiation rules, right? Because now we're doing the harder differentiation rules. So so hopefully we can do the easy ones. So the harder ones won't be so bad. Let me move my chat out of the way here so I can scroll up. All right. So last time we left with one problem, and so I want to finish that one before we go any further. So we had this function x minus 4 over x squared minus 7, and we were asked a geometric question about this problem, right? We wanted to know where on the graph of this function where the tangent line is horizontal, okay? And so we discussed this a little bit beforehand, right? Before we left last time. Tangent line is horizontal means turning points. So as kind of illustrated in this picture, but this is not, this graph is not the graph of this function. But in general, when you're looking for places where tangent lines are horizontal, you're looking for turning points, right? Okay. A tangent line is going to be horizontal where you have a turning point. Turning point, right, is a peak point or a valley point. That's where the curve is going to switch from increasing to decreasing, like you see here, or vice versa, where it switches from decreasing to increasing. So this is just kind of a roundabout way, kind of a backwards way of asking where are the turning points on this graph, right? Okay. And that's not easy to estimate just from looking at the graph. You certainly can look at the graph, and that's good, but it's not easy to look at the graph and figure out from the graph where the turning points are because this thing has a really wonky graph. So if you graph x minus 4 over x squared minus 7, you get this picture. So you get kind of a complicated graph, right? It's got 3 branches to it. There are actually 2 numbers that are not in the domain of this. There are 2 numbers on the x-axis that are not in the domain of this function. Actually, one of them is negative square root of 7, and one of them is positive square root of 7. So you're going to have breaks in the graph here at negative square root of 7, whatever that number is, somewhere between 2 and 3, right? And then over here, positive square root of 7, you're also going to have a break in the graph. So you get a complicated graph here with 3 branches. Now it does have some turning points though. You do have a turning point right here in this middle branch, and you know there has to be a turning point in this middle branch, right? Because notice this middle branch, this piece in the middle is switching from decreasing to increasing, right? See, this piece is decreasing and this piece is increasing. So since you switched from decreasing to increasing, that means somewhere that switch has to occur, right? And that switch is going to be the turning point. So we know, we can see somewhere in here, there's a turning point, right? somewhere there's a place where, this curve switches from decreasing to increasing, but it's very difficult to estimate looking at the graph where that is, right? It's somewhere in here, but I don't know exactly where it is. Okay, different people may get wildly different estimates just from looking at this graph. Now, it turns out there's another turning point as well, and that one is really hard to spot. It's over here on the far right. So notice this branch on the far right is increasing, and then it's really hard to tell what happens as you move further out the x-axis. It's really hard to tell, does it continue to increase, or what's going on? It's because this graph is really hugging the x-axis so closely, right, that it's really hard to tell what the behavior of the curve is as you get further out the x-axis. But as we're going to discover, actually it does increase and it does start to decrease again. Believe it or not, this thing increases to a peak and then it's going to start decreasing again, although it's almost impossible to see that behavior, and it's very hard to figure out where that switch from increasing to decreasing occurs. But that is the turning point. That's going to be the turning point. Well, thank God we have calculus, right? We don't have to figure this out graphically because we can do it with calculus. And that's the whole point of this question, right? Is how do we use calculus to figure out where those, how do we use calculus, right, to figure out where those turning points really are? Okay, so, all right, so that's kind of just a description of what we're doing, right? And so how do we look for those turning points, or where the tangent line is horizontal? Well, we sort of know how to do that, right? Because horizontal lines have what slope? Quickly?
0.
0, right. Horizontal lines have 0 slope, right? And Van, how do we find slopes of tangent lines? What gives us slopes of tangent lines? What tool gives us slopes of tangent lines?
The rate of change.
The rate of change function, right, or the derivative, right? Okay, so finding where the tangent line is horizontal means we're going to take the derivative f prime of x and we're going to set it equal to 0, right? Because we want to know where the derivative is going to give us a 0 slope tangent line, correct? And so it's a matter of solving this equation. But of course, we got to figure out what is f prime of x. So I have to go through the work of figuring out what is f prime of x from this formula, right? Oh, well, let's see. So f prime of x means I'm going to have to use the quotient rule, right, to find this derivative, because this derivative is it's a quotient, right? Okay, so so we have to remember the quotient rule here. So this is really mostly just practice with the quotient rule. All right, so you guys tell me the steps now for the quotient rule, right? What do I fill into the top? What goes in the top there? How do you start?
So you want to take the derivative of the top and multiply it by the bottom?
Yeah, take the derivative of the top, multiply it by the bottom. So this is a real easy function in the top, Donna. What is the derivative of x minus 4?
X.
Yeah, you're focusing in on the x, which is the right thing to do, but the derivative is even simpler. So yeah, what's the derivative of x?
1.
1. So, and the derivative of the minus 4 is 0. So the derivative of the top is just 1. That's really nice, you see, okay? So you just get 1 times the bottom, keep the bottom, which is x squared minus 7, and then minus, don't forget, in the quotient rule, you're subtracting, and then you flip that, right? So you keep the top, which is x minus 4, and multiply by the derivative of the bottom, x squared minus 7. Abdel, do you know what the derivative, of x squared minus 7 is? X squared minus 7? Abdel, are you there? You were there a moment ago. I've lost you. Okay. All right. All right, Abdel. So we'll ask someone else. I'm not sure who else is here. Let me look down my list.
I'm sorry, sir. You said Jocelyn?
No, I didn't. But Jocelyn, I will ask you though. I asked for Abdel, but I'm glad you answered because I'll ask you. What is the derivative of x squared minus 7? So, because that's the derivative of the bottom that we need to fill into the quotient rule, right? So, derivative of x squared minus 7. What's that derivative going to be? So remember, you can, Jocelyn, you can take it term by term, right? So first, just what's the derivative of x squared?
X squared.
Yeah, x squared. But what is that's the expression? But what's the derivative of x squared? This thing. What's the derivative of x squared? You remember the power rule?
It would be like the 2 to the power of x.
Yeah, well, 2 times x, right? So you bring 2 down, right? So you bring 2 down, and so you get 2 times x, and then you subtract 1 from this exponent. Well, 2 minus 1 just gives you 1. So you don't have to write exponent 1. So you just get 2x there, okay? Yeah, so the derivative of x squared is just 2x. And Yasin, what's the derivative of 7? That's a constant. So remember, for constants, what's their derivative?
Cos.
Yeah, just a plain number without an x in it. What's its derivative going to be?
It's usually 0.
It is not usually. It's always 0. Okay.
It's always 0. Sorry.
Yeah, it's going to be 0. So so the 7 you can just ignore. So the derivative of the bottom, because it just turns out to be 2x. Okay. Mm-hmm. Now, Jocelyn, in the quotient rule, do you remember what goes in to the bottom of the quotient rule? What do you put in the bottom there?
Over 1.
The top. What now?
Over 1.
No, I wish it were 1. That would make our life easier, but unfortunately, it's not 1. It comes out more complicated than that, right? So in the quotient rule, when you're finding the derivative of the quotient, that's what you put into the top. And then what goes in the bottom here? It's going to be the original. This is always true. So it's just the original bottom, which is x squared minus 7. And then you have to square that.
Yes.
So you take the denominator and then you square it. So this is what the derivative is going to end up looking like to us. Okay. And remember now, we're going to set that equal to 0. Because we're trying to figure out, what x values will give us a derivative of 0. It's going to be those x values where the tangent line is horizontal. All right, so so now this looks like a terrible equation to solve, but let me tell you, it's not that bad, okay? So do not start freaking out or getting intimidated right here, okay? First, you want to simplify the numerator a little bit. So go ahead and remove the parentheses by doing the multiplication, do the subtraction. So you would get 1 times x squared minus 7. Well, that's easy. That's x squared minus 7. And then you're going to have x minus 4 times 2x, but don't forget there's a minus sign here. So x times 2x is 2x squared, but it's minus. So you get minus 2x squared. And then minus 4 times 2x is minus 8x, but you have a minus on that. See, minus 4 times 2x is minus 8x, but minus that makes it plus. So you end up with plus 8x. And then just leave the bottom as x squared minus 7 squared. Don't try to multiply this out. And now combine your like terms. So you get x squared minus 2x squared. So that's minus x squared. And then a plus 8x. And then a minus 7. And then you just keep that x squared minus 7 squared. So now we're down to this equation to solve. Still looks like a terrible equation to solve, right? Okay. How am I going to figure out what x values make this equal to 0? That looks like a really hard equation to solve. But now here's where we can use our logic to make our life easier here. Look, when you have a fraction, this is a big fraction, right? So when you have a big fraction that equals 0, the only way a fraction is equal to 0 is if the top is 0. Think about that, okay? If you have a fraction that's equal to 0, the only way that fraction is going to be 0 is if the top is 0. The bottom cannot be 0 because you cannot divide by 0. So in solving this equation, we can just ignore the denominator. It's the top that we're interested in. So really we just have minus x squared plus 8x minus 7 equal 0. That's looking a lot more doable. That is a quadratic equation. See, it's got x squared in it, and we've solved lots of quadratic equations. So now we're on much more familiar ground, right? We have a much better idea of how to solve quadratic equations. How do we solve quadratic equations, by the way? There's really only a couple of basic strategies. What are the basic strategies for solving quadratic equations? We've already done it several times in the class. So what are our choices there? What would be our first choice? Well, my first choice. I hope you'll say the same thing. But what's our first choice for solving a quadratic equation? What usually do you try to do first?
Factor.
Factor, yeah. So it's the F word. Okay. So always keep that in mind. All right. It's factoring. All right. So now that doesn't always work, but you want to try that first. Now, it's not easy to factor when you have a negative x squared. That would be better if that were positive. So I'm going to make that positive by multiplying both sides of the equation by -1. I'm going to multiply both sides. You can multiply both sides of the equation by anything you want other than 0. You can't multiply by 0, but you can multiply by any other number. So I'm going to multiply both sides of this equation by -1. Now, don't forget to multiply every term, though. So -1 times minus x squared gives me positive x squared. That's what I want. -1 times positive 8x is minus 8x. And then -1 times -7 is +7. And then don't forget, also multiply the -1 times 0. But that's not going to make any difference because -1 times 0 is still 0. See, this looks like a much more friendly quadratic equation for factoring. And that one does factor. So that's nice. It does factor as x minus 7 times x minus 1. So we get a lucky break. We can solve this by factoring. And it turns out then that either x minus 7 is 0 or x minus 1 is 0. And this means x is equal to 7 or x is equal to 1. So there are your two x values, 7 and 1, that make the derivative equal 0. So it's going to be at x equals 1 where you're going to have a horizontal tangent line, and it's going to be at x equals 7 where you have a horizontal tangent line. Let's see if that kind of agrees with what we see on the graph. Kind of. It's hard to see, right? So right there at, let me see if I can get it. Yeah, there it is. Right there at 1, there is, at x equals 1, there is your, there's where you're going to have a horizontal tangent line. So that is a turning point for this. That's a turning point for this function. It switches from decreasing to increasing. It's very subtle, but it does. It switches from decreasing to increasing right here at x equals 1. And the other one is 7, which is almost impossible to tell, but right there at 7, there it is, right there at 7. And the y coordinate turns out to be 0.071 approximately, but right there at 7, that's where the tangent line is also horizontal. So it's very subtle, but it switches from increasing to decreasing right here at 7. That's the other turning point. By the way, you can tell that if you go a little bit to the, notice right here at this turning point, the local maximum is 0.071. If you go over here to say 6, I want you to notice the y coordinate goes down. The y coordinate's a little bit smaller. See that? It's right there at 6. I don't think I can get 6 exactly. Oh, there it is. See, notice the y coordinate is 0.069, a little bit below the 0.071. Or if you go over here to 8, notice the y coordinate goes down again. Can I get 8 perfectly? Yeah, there's 8. See, notice at 8, the y, well, I messed it up. But notice at 8, the y coordinate is, I can't get it again. But at 8, the y-coordinate was 0.07, which again is a little bit less than 0.071. See, so you have a peak right here at, not much of a peak, but you have a peak right here at 7. That's where the tangent line is horizontal. Okay.
I have a question.
Yes.
So on the graph, it just by looking at it, we think that there should be 3 turning points, but we only got 2. Does that mean the third line just doesn't have a turning point or a tangent?
This piece? Yeah, yeah. So apparently the branch over here on the left does not have a turning point, or we would have found it. So so this one, oh, see, it's so subtle because you can go, it's really a long way here, but there is no turning point. So that means this branch is always decreasing. It's always decreasing. So apparently if we go far enough to the left, I don't know how far we have to go, this branch is going to keep going up. It's not going to ever start going down again. So it keeps going up. It's just rising very slowly to the left. So if you go way out the x-axis to negative infinity, get close to negative infinity, this branch will go high, but it's just increasing very slowly to the left. So yeah, so no turning point, because if there were a turning point, we would have found it. It's just not there. See, calculus really helps us there. You're thinking on the left, what's happening to this curve on the left? It's so close to the x-axis, I can't tell. Turns out it's getting as you move further to the left on the x-axis, this curve is continuing to go up. Okay. All right, so I'm gonna this example I'm not gonna do. I had an applied example, but we'll skip that one in the interest of time. And so I want to talk to you now about the what's called the second derivative. So and conceptually this is easy. Conceptually, it's easy to understand what the second derivative is, but now how we use it in practice is more difficult. But the basic idea is easy. The derivative function, if you have a function, right, its derivative is a function. See, so if you start with a function, just any old function, right, and its derivative is also a function, but that means since its derivative is a function, you can take the derivative of the derivative, okay? So, right, okay, because the derivative is itself just a function. So when you take the derivative of the derivative, that's called the second derivative, not surprisingly. And we denote it in function notation by using 2 prime marks here, right? Because the derivative is f prime. So if you take the derivative of the derivative, you're taking the prime of the prime. So that gives you 2 prime marks here, right? 2 apostrophes here, okay? So that's our function notation for the so-called second derivative, the derivative of the derivative. And actually, we can continue this process. So we can take a third derivative and a fourth derivative, and actually we can take as many derivatives as we like. Okay, so we can continue this differentiation process indefinitely. Okay, but for right now, we're just going to focus on the second derivative. Now, the second derivative does have important geometric interpretation, okay, but it'll take us a while to understand that geometric interpretation, okay. But so remember but let's just briefly refer to that. So the first derivative tells us the rate at which a function is changing, right? Increasing or decreasing, right? So first derivative tells us if a function is going up or as a function is going down. The second derivative tells us the rate at which the rate of change is increasing or decreasing, right? Okay. All right. So see that that gets kind of subtle, right? So remember, the first derivative is the rate of change. The second derivative is the rate of change of the rate of change. And sometimes that's kind of hard to think about. In practice, though, you often think of the first derivative as speed or velocity. So we've already used, right, the idea of the first derivative as speed or velocity. The second derivative is often interpreted as acceleration, okay? See, velocity tells us how fast an object is moving, right? How fast an object is changing. Acceleration tells us how fast velocity is changing, right? If you're accelerating, your velocity is increasing, right? Okay. If you're decelerating, your velocity is decreasing. Well, so the second derivative tells us the rate at which the velocity is increasing or decreasing. So that's why we often think of the second derivative as acceleration. So first derivative, you can sort of think of it as velocity. Second derivative, in practical terms, you can think of the first derivative as velocity and the second derivative as telling us acceleration. So that's kind of very rough terms, all right? We'll actually use the second derivative in lots of different ways, but that's a good way to sort of initially think about the what the second derivative means. Okay, well, let's just practice computing second derivatives first, but that's easy, all right? So, so let's try computing some second derivatives of some functions. All right, so here we have this function, f of x is 2x cubed plus x squared minus 13x plus 6, right? Okay, and so that's what we want to do is find what is this, not the first derivative, but the second derivative of this function. However, to find the second derivative, you're going to have to start by finding the first derivative. So you have to go through the first derivative to find the second derivative. So, so first let's find the first derivative, and that's easy to do using the power rule here, right? So just go term by term. The derivative of 2x cubed is 3 times 2 times x squared, right? Bring the 3 down and subtract 1 from it. And then the derivative of x squared, as Jocelyn told us a moment ago, that's just going to be 2 times x, right? And the derivative of minus 13x, that's going to be just minus 13. And of course, the derivative of 6 is 0. So, so that won't contribute anything to our, that 6 doesn't contribute anything to our derivative. So there's the first derivative. Let's simplify that a little bit. That's 6x squared plus 2x minus 13. And now let's find the second derivative. So that's so easy, right? The second derivative, you denote that by using the double prime notation. And that's just the derivative of the first derivative. So, so the derivative of 6x squared is going to be, bring the 2 down, right? So you have 2 times 6 times x to the first power. And then the derivative of 2x is 2. And then derivative of minus 13 is 0 because that's a constant. So you just end up with 12x plus 2. That's it. So pretty easy, right? Okay. Just the derivative of the derivative. And again, we can continue this process indefinitely. So we can calculate the third derivative, which you denote with 3 primes here. And that's just, the third derivative is just the derivative of the second derivative. What's the derivative of 12x plus 2 going to be here? That's easy. So what is the derivative of 12x plus 2? Someone?
12.
12. Yeah, just plain 12, right? Okay. So you can figure that using your differentiation rules, right? The derivative of 12x plus 2 is just 12. But you also know that this derivative is going to be 12 because 12x plus 2 is a straight line, and the derivatives of straight lines are always the slope of the line. And the slope of 12x plus 2 is 12. So there's another way of thinking about why the derivative of 12x plus 2 is 12. So see, the third derivative here is a constant. You just get just a plain old number 12, okay? And if you took the derivative of the third derivative, you would have the fourth derivative, and so on and so forth, okay? All right. Well, I'm going to let y'all try one now, okay? So let's see if y'all can find the second derivative of 4x to the 3/2 power. I'll show you how to write that down in I'll show you how to write that down, how to indicate second derivative in two different ways here. One way is going to be using the prime notation. So you can write y double prime for the second derivative. But there's also the more old-fashioned way of writing down of indicating second derivatives. I'll show you that after you do that, though. All right. So first, find for me here what is the second derivative. Remember, you have to start with the first derivative. Okay. So this is a two-step process. All right. All right. So y'all try that one. Everyone try that one for me. I'm going to choose someone to help us or to show the class. Someone who I need to ask the question of, but most of y'all have already responded several times. So I'm running out of names here. You don't necessarily have to worry about simplifying your answer too much. Okay, I'll show you how to simplify it. Just try to get down some answer for the second derivative. Yeah, everyone is answered for me.
Do you want me to give the answer?
Hang on a minute.
Okay.
Was that Mohammed?
Yeah.
Yeah. Okay. So in a second, Mohammed, I'll get you to answer that. All right. We'll give everyone a chance to get something written down. Okay, all right. So if you didn't get finished, that's fine. Just if you made some progress there, that's good. And but Mohammed's going to help us with writing down the second derivative. So of course, Mohammed, we have to start with the first derivative. So what is the first derivative here?
The first derivative is 6x to the power half.
So how did you get that? Can you just tell me the steps a little bit so I can
multiply the 3 by 2 times 4. That's how I got
so you're bringing the 3 halves down times the 4 and then times that 2. You said what?
And 3 by 2 minus 1. So to the power.
Yeah, to the power what?
To the power half.
Yeah, because we take 3 halves minus 1, right? But 3 halves minus 1 is 1 half, correct? And so then you took the 3 halves times the 4, and that turns out to be 6, right? So we get 6x to the 1 half power, which, by the way, is this. This is not that important, but just as a reminder, remember x to the 1 half is square root, right? So this is really the same as 6 times the square root of x, okay? But that's not important. So now we find the second derivative, right? Mohammed, so what is the second derivative going to be?
The second derivative, I got 3 over x to the power half. So right, I multiplied half with 6. But
so you brought the 1 half down times the 6, and then you got x to the, and this is kind of the tricky part. What?
I got x to the power negative half by minusing 1 from there.
Right. Yeah. So 1 half minus 1 is going to end up being negative 1 half, right? And so that's a little bit ugly, but that's it, right? So 1 half times 6 is 3, And then how did you simplify the x to the minus 1/2?
So when I take x to the denominator, the sign changes.
Exactly. So you end up getting 3 over x to the positive 1/2, okay? And you can leave it just like this, that's fine. But because that's the way the original problem was written, it was written using fractional exponents. But you could also write this as 3 over square root of x, because x to the 1/2 power is square root of x, right? Okay, so but it's fine leaving it like this, because that's kind of looks like what the original problem was written, right? So we can use this modern prime notation to indicate first and second derivatives, or higher order derivatives like third derivative as well. But let me show you the old-fashioned way of writing, of indicating a derivative. So you know another way of indicating the derivative, the old-fashioned way, is writing dy over dx, right? Okay, that is another way of indicating first derivative. So dy over dx is the same as y prime. So using this notation to indicate second derivative, it comes out looking kind of funny. You're going to use a superscript of 2, so it looks like an exponent of 2, right? That's where that's how you indicate second derivative. So, but in the numerator, you put the 2 by the d, above the d, but in the denominator, you put the 2 by the x. So notice that subtle shift there. The second derivative is you can read this as d squared. It's not really squared, but you can read it that way. D squared y over dx squared. That is that's the old-fashioned method from the beginning of calculus for indicating second derivative. Okay, but notice that and there's a reason why there is a logic to why the exponents are in a different position, but I'm not going to go through the explanation for that. Okay, so it's d squared y over dx squared. That means second derivative in the old-fashioned notation. All right, I'm going to let y'all try another one. Okay, right before we break here, and well, maybe we'll do this after the break. But so y'all can think about it during the break. So I also want to find the second derivative of secant. All right, the second derivative of secant. So I'll give you a little bit of a head start here. Remember, you got to remember the first derivative of secant, right? And so you may not have memorized that one yet, the derivative of that trig function, but the derivative of the first derivative of the secant, you'll recall we learned last time, is secant x times tangent x. So hopefully you're on your way to memorizing the derivatives of the trig functions, one of which of course is secant x, you know, not one of our most used trig functions, but it's important. And its derivative is secant x times tangent x. All right, so to find the second derivative, you're going to have to find the derivative of secant x times tangent x. All right, so we're going to try that as a class in a minute here. So let's take a break here for 4 or 5 minutes, right? Okay, and we'll come back a little bit after 12:30, and we'll look at this problem and then another example or two of second derivatives. We're going to explore second derivatives more thoroughly a little bit later, but right now we're just sort of introducing what's the idea of the second derivative. Okay, so let's break there. Okay, I'm resuming the recording. So let's discuss the second derivative of the secant, and not that we'll use the second derivative of the secant all that often, but this is a good example for illustrating second derivative anyway. So we had already written down the first derivative, right? Because that's just a derivative of one of the trig functions, and we want to memorize those derivatives. So the derivative of the secant is secant tangent, but now the trickier part here is to determine, well, what is the second derivative? So in other words, what is the derivative of secant times tangent, right? Okay, so now That one's a little bit trickier because that involves this expression secant times tangent. So so we have to think about how we're going to approach that. What a differentiation process is going to help us with finding that derivative. So Krishna, are you there? I see you there. You're logged in. Can you respond? What I want to know is which differentiation rule would we use to find the derivative of secant times tangent? What differentiation rule is convenient for us to do that? Hi, Krishna.
Yeah, I am here.
Uh-huh.
I'm here, but not gonna lie, I don't know.
Okay, well, so I'm just going to help jog your memory, right? Okay, because this is just something that that you probably just need to be reminded of a little bit, right? See, here you have two expressions multiplied together, right? You've got the secant here, and then times the tangent, right? Okay, so we've got two expressions multiplied together. So which of our rules that we've seen so far help us when we've got two expressions multiplied together? When you multiply two expressions together, what's that called? It begins with a P. Can someone remind Krishna of what's it called when you multiply two expressions together, Van?
Product.
Product rule. That's called a product, right? Okay, so Krishna, you heard that? That's a product. So we'll see. So maybe that will tip you off there, right? So which rule can we use to help us find the derivative then? The which rule?
Wait, sorry, I couldn't hear because my connection kind of disconnected for a second.
Okay. All right. So Van said that when you multiply two things together, when you multiply two quantities together, that's called the product, right? Okay. But now when we hear the phrase product and we're thinking about finding derivatives, oh, that reminds us we can use the which rule? Okay, well, it actually is the product rule. Okay, yeah, there's a rule called the product rule that's exactly set up for finding, Krishna, that's exactly set up for finding derivatives of products. Okay, so that's what you would want to sort of clue in on when you're looking at this. You would want to think, oh, I've got a product here, and so I can use the product rule to help me find that derivative. Okay, so be thinking of clues like that, right? I have a product, so I can use the product rule. Or notice in this next example that's coming up, we have a quotient, right? Because we're dividing two things here, so we can use the so-called quotient rule. All right, so Krishna, that's what we want to use is the product rule. Now let's see if you can remember how the product rule works, right? So when you've got two things multiplied together and you want to find the derivative, remember there's this kind of alternating process, right, for finding the derivative of a product. Do you recall that?
No.
Yeah. Okay. All right. So this is where the homework that's due on Saturday will help you a lot. You'll have this memorized really quickly. Can someone remind Krishna of that? Right. So what are the steps for applying the product rule, which is what we're going to apply here? Okay. So what do we do in what order? Abdel, do you know what in doing the product rule here, what we do?
I'm not sure either.
Okay, all right. So so pay close attention here, Abdel, because this is really going to be helpful to you in the homework, right? Okay. So who else wants to just say what those steps are, right, to apply the product rule? It's kind of a little process you go through. You could almost make a little jingle or a song here. I won't attempt to create one, but you can probably make a song out of this to help you remember how the product rule works. Okay. Who wants to tell us? goes really fast, right? So what do we do? Van, are you going to help us
We
again?
set them as two different.
Wait, say that again.
Set them as fx and hx, I guess.
Oh, I can't. I didn't understand what you were saying.
Oh, I said that we set them as two like different equation, and then there's the like the secant and x times the derivative of the tangent.
Oh, there you go. Right. So since you've got two different things multiplied together here, you've got two expressions multiplied together, right? Okay. Then remember, you sort of alternate taking the derivative, right, Van? Okay. So,
yes.
So which derivative do you take first?
I guess a secant.
Secant, right. So first, take the derivative of the secant, and then you just keep the tangent, right? So, well, what is the derivative of the secant? Oh, we just talked about that, right? The derivative of the secant is secant x, tangent x, right? So take the derivative of the secant, that's secant x, tangent x, and then keep the tangent. Don't do anything with that, okay? So you get the derivative of the secant, which is secant x, tangent x, and then keep this tangent. So this tangent is the same as this one. This part is the derivative of the secant. Okay, that's the first step. Now, what do you add on here in the product rule? You just reverse this, right?
Yes.
So keep the secant, then keep the secant. So keep this secant, and then multiply by the derivative of the tangent. But now we have to remember what the derivative of the tangent is. What's the derivative of the tangent, though? What?
Secant square.
Secant squared, right. Okay, so that's another one. That's one of those basic trig functions you just have to remember the derivative of. So the derivative of the tangent is secant squared. So we end up with, well, this is a little bit messy, but you know, it's not terrible. Secant times tangent, you can write that as secant x times tangent squared x, since we're multiplying tangent times tangent. And then here we have secant x times secant x. Well, I guess that is, I guess that's secant cubed x, right? So we have plus secant cubed x. Well, so there it is. Okay, there's the second derivative of the secant. That's it. Okay, unless they ask us to do something with the second derivative, there it is. You've got it. There it is. You've got it written down. Okay. All right. So Krishna and Abdel, y'all saw that, right? Okay. How that works, right? That's how the product rule works. Derivative of the first thing you're multiplying, right? Keep the second, then plus, just reverse that. Keep the first and multiply by the derivative of the second one. All right. Okay. Oh, now let's look at this part D, because this one looks awful. Okay, because here we're going to calculate a derivative, a second derivative, but we're going to have to use the quotient rule. And you know the quotient rule, right? That one's really nasty, right? So well, but anyway, it is what it is. So let's see if we can find the second derivative of this quotient. Okay, so we're going to have to be patient with our algebra here. So let's start with the first derivative. I'm going to use the old-fashioned notation, dy over dx, to indicate the derivative. Okay, so it's derivative of quotient. So we have to use the quotient rule. So the quotient rule is very similar to the product rule, but not the same. Remember, in the quotient rule, you keep the denominator, the x minus 4 squared, but you square it. Okay, so you have x minus 4 squared, and then the top is the part that looks like the product rule, with just a slight difference. So in the top, you'll write the derivative of the top times the bottom. So take the derivative of the top, keep the bottom. The derivative of x squared plus 3x is 2x plus 3. And then I keep the x minus 4. So I'm just using the power rule here to find the derivative of x squared plus 3x. Bring the 2 down, that gives us 2x, and the derivative of 3x is 3. And then keep the x minus 4, and then minus, and then you reverse that, right? So keep the top, the x squared plus 3x, and then multiply in the derivative of the bottom. But that's really convenient here because the derivative of x minus 4 is 1. The derivative of 1x is 1. And the derivative of minus 4 is 0 because that's a constant. So, so that makes our life a little bit easier. So maybe this is not as ugly as I was afraid it's going to be, but it's pretty ugly. Okay, so that's just the first derivative. But remember, we want to calculate the second derivative. Let's simplify this a little bit. Maybe it won't turn out so. Maybe when I multiply these parentheses together and add like terms, maybe it won't turn out so bad. 2x plus 3 times x minus 4. Let's see, that's going to be 2x times x is 2x squared. Then you have 2x times minus 4, that's minus 8x. And then you have 3 times x is 3x. And then you have 3 times the minus 4, that's minus 12. And then minus, of course, the 1 here doesn't make any difference at all. You're just subtracting off what's in the parentheses there. So that's minus x squared minus 3x. Be sure you distribute that minus sign over x minus 4 squared. Now you can add your like terms together. So what do we end up with here? This big mess. 2x squared minus x squared is x squared, right? And then minus 8x plus 3x minus 3x. Well, these 3x's cancel. So you just get minus 8x and then a minus 12. That minus 12 is left there over x minus 4 squared. Okay, all right. See, that was already hard enough. And that was just the first derivative, my word, okay? So that's just the first derivative. So now we have to go on and find the second derivative. So I have to do this process all over again. Yeah, Donna?
So there's a 1 at the top, but you left it out. Don't you have to subtract that from the negative 12?
Don't I have to, this one?
Yeah.
That's times 1.
Oh,
right?
Sorry.
So,
okay.
it's essentially invisible, right? Okay, you don't really have to worry about it.
Sorry, I thought it was subtraction. Okay, got it. Thanks.
All right, Donna, but now, Donna, this second part really is ugly. So now I want to find the second derivative. So this is the way you denote the second derivative in the old style notation, d squared y over dx squared. And so I'm finding the derivative now of this, because that's the derivative of the first derivative, okay? So, man, that's going to be tough. So, all right, so how do I do that? I have to use the quotient rule again, okay? I'm going to have to use the quotient rule again. So, so the bottom I can do, because the bottom of the quotient rule says you're going to take this denominator, right? And you're going to square it. So you would have x minus 4 squared squared. Let's write that down, but we're not going to really simplify it much. So I have x minus 4 squared. That did not, but then I have to square it again. So I have to put another square here. But x minus 4 squared is just x minus 4 to the 4th power. So that's not really all that bad, the bottom. You just end up with x minus 4 to the 4th power. Because when you square something and square it again, it's just the same as raising it to the 4th power, okay? Now we have to find out what the numerator is, and that is going to be a little bit ugly. So let's see, we take what? The derivative of the top times the bottom, okay? So your top is x squared minus 8x minus 12 times the bottom. Well, that's not too bad. The derivative of x squared minus 8x minus 12, that is 2x minus 8. See, the derivative of the top here is 2x minus 8, and then you multiply it by the bottom. So x minus 4 squared. So the whole bottom is squared, right? And then you subtract off, and here's the tricky part. You keep the top, which is x squared minus 8x minus 12. So we'll just keep that. But then we have to find the derivative of the bottom. So I have to think about this. So I'm going to have to stop here for a moment and think about what is the derivative of x minus 4 squared. The easy way to find the derivative is to go ahead and square out the x minus 4. So multiply it by itself to expand that square, expand that product. X minus 4 squared means x minus 4 times x minus 4. Well, when you multiply x minus 4 times x minus 4, you're going to get x times x is x squared. And then you're going to get minus 4x twice. Minus 4 times x, and then another minus 4 times x. So that's minus 8x. And then minus 4 times minus 4 is plus 16. So x minus 4 squared is the same as x squared minus 8x plus 16. And it's easy to find the derivative of x squared minus 8x plus 16. That derivative is going to be just, what, 2x minus 8. And there it is, okay? So there is your, I haven't simplified it, but there is your second derivative, okay? So if you want to go ahead and multiply all these parentheses together and add like terms, you can do that and simplify the numerator. I'm not going to go through all those steps now, so I'm just going to leave it in this kind of raw form because we don't have time to multiply out all those parentheses. So I'll just leave it as 2x minus 8 times x minus 4 squared minus, and then the x squared minus 8x minus 12 over 2x, times 2x minus 8, okay? But with more time, we could go ahead and multiply these parentheses together, collect like terms, and it would look a little bit nicer. Not that great, but it may maybe look a little bit cleaner, okay? So, you know, finding second derivatives with the quotient rule, you know, sometimes that's ugly if you have to apply the quotient rule twice, right? Yeah, that's just life, okay? That's just the way it comes out sometimes. All right, let's look at a quick applied example, and then really fast here. This one is pretty easy. So this one says an astronaut, so this is our famous falling object problem again. But now the astronaut is dropping a tool on the moon, okay? And so maybe this will be relevant soon because, you know, there are plans now, right, to send people back to the moon. So that hasn't happened since the 1970s, but they're gearing up now to do that in the near future. I don't know, not within the next year or something, but in the near future. All right, so, but in our imaginary problem here, an astronaut drops a tool exploring the moon, all right? So now look, objects fall on the moon, you know, according to the same gravitational laws, right, that govern objects falling on Earth. But the moon, of course, has less mass, so the equation looks slightly different on the moon than it does on Earth, but the basic equation is the same, okay? So here's the equation for this tool dropping. So this is the formula that gives you the position of the tool, right? Okay, after it has been dropped by the astronaut, okay? All right, so so t here is elapsed time in seconds, and the y value is the height of the tool in meters, okay, after it's been dropped. Okay, so all we want to do is evaluate a y of 1, okay, and then y prime of 1. So the first derivative evaluated at 1, and then the second derivative also evaluated at 1. So that's pretty easy, right? That's just a matter of computing the first and the second derivatives. The hard part here is trying to interpret these values, okay? Well, the values are also not difficult to interpret except for the last one, the second derivative. What does the second derivative mean, okay? All right, so let's start here. We have the original formula, right? Again, this gives us the position or the height of the tool in meters. So when you evaluate y of 1, what you're actually calculating is what's the height of this tool after 1 second, right? So that's very easy to interpret, okay? Let's calculate what y of 1 is. It's also easy to calculate. So we get minus 0.81 times 1 squared plus 2. And I think that's going to be what? Minus 0.81 plus 2, which is what? 1.19. So, so that's easy calculation too. So what this tells us is what? After 1 second, right? Okay, the tool is 1.19 meters off of the ground. Okay, so we can write that in. So after 1 second, guess we wouldn't say off the ground. We would say the height of the tool, right, is 1.19 meters. So that's really just kind of an algebra question, right? No calculus there involved. All right, now we also want to calculate y prime of 1. So that means I have to know what is the formula for y prime. But that's an easy application of the power rule, right? So you just bring the 2 down times the minus 0.81, right? And then subtract 1 from the exponent. So you get minus 0.81 times t. And the derivative of 2, of course, is 0. So you get this really nice, easy formula. What is that? Minus 1.62 times t, right? Am I doing that right? I think so. So there's a nice easy formula for the derivative, and it's easy to evaluate that derivative at 1. Just plug 1 in for t, and so you just get what? Minus 1.62. Okay, so y prime of 1, or the derivative evaluated at 1, is minus 1.62. Now, however, what does that mean? Okay, so what is the minus 1.62 telling us? All right, so remember, this is derivative. Derivative is rate of change, right? So how would we explain to someone what that number minus 1.62 is telling us, okay? So it's going to be after 1 second, obviously, because we evaluated the derivative in 1 second, right? But after 1 second, what is the case? So how do we interpret that rate of change? We practice this a lot now, right? So y'all should be very good at saying what that means, right? How do you interpret that rate of change? Remember, first derivative is often interpreted physically as velocity. Okay, so if you remember that idea, it's very easy to explain what the minus 1.62 means. Does someone want to tell me that? Someone want to check mark the gold star there? This is how you get your 100 class participation grade really easy. Okay. If you looked at your WebAssign grade book, you'll see that 100 class participation grade really helps your average, I think. Okay, so that's a good thing to have in there. So what is the minus 1.62?
The speed of the falling object after 1 second.
Yeah, so yeah, it's something to do with the speed of the falling object after 1 second, Donna. But but make that more clear. I need you to work the 1.62 into your answer.
So after 1 second, the tool was falling at a speed of negative 1.62.
Yeah, so it was falling. So so the tool, since it's falling, you don't have to include the negative in your answer. So the tool was falling by what now? 1.62 watts.
Meters per second.
There you go. Right. Perfect. Meters per second. Yeah. See, this is a rate, right? So it's like miles per hour is a rate, correct, right? So make sure you get that rate into your answer. So after 1 second, that's how fast the tool is dropping. 1.62 meters per second. That's its velocity. Okay. So it's dropping, that's pretty fast, 1.62 meters per second, right? Not super fast. You can visibly see that, but pretty fast. Okay. All right. Now let's so the moon has a fair gravitational force, right? Let's see now what the second derivative, and see if we can interpret that. That's harder to interpret, but it's not difficult to calculate. What is the second derivative? So the second derivative is the derivative of the first derivative. So there's your first derivative. We look back up there. There's the first derivative. So what is the derivative of that formula? Yeah, what's the derivative of minus 1.62 t?
Isn't it just negative 1.62?
Yes, it's minus 1.62. So you just end up with a really simple formula for the, Lance, you just end up with a really simple formula there for the second derivative, right? It's just a constant, okay? You really can't get much easier than that, okay? So minus 0.162. Now, here's the hard part though, Lance. So you're on the spot here. So you have to explain to us what, well, we have to evaluate that at 1. But since that's a constant, when you plug 1 in here, you just get the same constant, right? So y double prime of 1 is minus 1.62 still, right? In fact, y double prime of anything is going to end up being minus 1.62. Okay, so wow, our height. So now how do we explain this? Okay, so so we can start it pretty easy. It's after 1 second, right? What's happening?
Well, second derivative is just like the second rate of change, right?
Yeah, so something is falling or something is decreasing, right? Okay, but what is it that is decreasing? It's not the tool, okay? The tool is definitely falling after 1 second, right? Okay, but that's not what that's what the first derivative tells us, right? That the tool is falling after 1 second. But after 1 second, what does the second derivative tell us is falling? Because see, this is negative. So something is decreasing, something is falling, but it's not the tool. What is it that's falling?
Oh, it's the speed, right?
It's the speed, right? Okay. So the velocity, or the rate of change, you could say, which is the velocity, is decreasing because this is negative by what?
It's just by negative 1.62, right?
Yeah. Well, we have the decreasing there, so we can write 1.62, right? And now, wow, what is the so what's the unit of measure here? Okay. Well,
meters per second squared.
Yeah, it's meters per second, but it's per second, okay? Because you see, that is the velocity is meters per second, right? Okay, so that velocity of meters per second is decreasing by 1.62 per second, okay? Wow, so what is that? When you say velocity is decreasing, you're often thinking of something slowing down. But in this case, the tool is not really slowing down, okay? Right, Lance? The tool is not slowing down. It's actually dropping faster, okay? Because this velocity is getting more negative,
Yeah,
right?
it's acceleration, right?
Yeah, it's actually accelerating, but it's accelerating in dropping. So the downward velocity is really getting higher. So another way to explain that is after 1 second, right? It was dropping by 1.62 feet per second, right? Okay, but it's also accelerating, right? So that means then that after 2 seconds, how fast would it be dropping? You would add on another what?
Wouldn't it just be that squared?
Not squared, but just doubled. Okay.
Oh,
yeah. All right. So if it were dropping 1.62 meters per second after 1 second, according to our second derivative, that means then that it's in another second, it's going to be dropping that much faster, right? It's going to be dropping, it's going to lose another 1.62, right? Okay. From its velocity. So after 2 seconds, it would be dropping by double this, you see, okay? After 3 seconds, triple that, right?
Yeah.
So so it's actually dropping after 1 second, it's dropping, right? Okay, but it's going to be dropping even faster because of what the second derivative is telling us, okay? See, that velocity is getting more negative, means it's dropping even faster, which of course is how falling objects work, right? Okay, as they're dropping at a particular rate, but then the further down they go, the faster they drop, right? Okay, so the more negative their velocity becomes. All right.
So the acceleration is increasing as it drops, or is the velocity and the acceleration is constant?
The acceleration is constant.
Okay, I see.
Because the second derivative is constant. So that means that as it's dropping, it's dropping faster and faster, okay? Always according to this number.
Got it.
Yeah. But the negative is what's making it confusing here, because the negative means it's dropping, but it's dropping faster, okay? Negative velocities mean it's falling, okay? And this means it's going to be falling even more rapidly as it continues dropping.
Okay.
Okay. So again, when you're thinking of second derivative, remember that is an acceleration. That's the change in the velocity. Velocity is the change in the height. Second derivative is the acceleration. That's the change in the velocity. Okay. All right, so I'm going to show you now, we're through with these notes, but we've got one more really important differentiation rule, very powerful differentiation rule called the chain rule. And with the product rule and the quotient rule and and of course we know how to differentiate trig functions. Once we memorize all those rules, we know how to differentiate trig functions. So when you take the differentiation rules that we've learned so far, and then you throw in the chain rule, which is the one we're just getting ready to start, then you will really be able to differentiate almost any formula that you are given, okay? So you are sort of know everything there is to know about differentiation once you've mastered the chain rule, along with the product and the quotient rule and the other rules that we've learned. Okay, almost, not quite, but almost any function that you're going to run into, you'll be able to differentiate. Okay, so you're really going to be an expert in differentiation, at least the mechanical process of differentiation. Now, applying derivatives to answer a question, that's more subtle, but at least carrying out the process of finding a derivative, you're going to be very good at that once you learn the chain rule. Okay. All right. Now, here's where the chain rule applies. Okay. And the chain rule is actually easy to use, but it's sometimes hard to recognize when the chain rule applies. That's going to be the hard thing for you to understand, is when to use the chain rule. It's not how to use the chain rule, but when to use it. Okay. But So only thing, of course, that's going to make you comfortable with that is lots of practice. But here's kind of the basic explanation. So if you have a function, right, that you can think of as the composition of two simpler functions, then you can find the derivative of that composition function by using this so-called chain rule. Okay, so now let's think back just briefly to what composition means, right? Remember, when you compose two functions, that means you take one function and you feed it as input to a second function. That's kind of what's expressed here in this statement, all right? So here I have a function called g of x. That could be any sort of formula at all. So I have this function g of x, and now I'm going to use that formula as input to a second function f, right? So when you feed one function as input to a second function, that process is called composition. And usually we refer to this input function as the inside function. I guess you could call it the input function, but usually we refer to it as the inside function because it's kind of inside this outer set of parentheses, right? And then this function f that's on the outside here, we often call that, this is informally, we call that the outside function. So the chain rule applies when you have an outside function that you are applying to an inside function, okay? And what the chain rule says is very easy to remember. You take the derivative of the outside function, you take the derivative of the function f, and then you just multiply in, that's all, the derivative of the inside function. So it's actually even easier than the product rule, okay? Right, so you take the derivative of the outside and multiply times the derivative of the inside. Right, so it's really a very simple formula. But again, the tricky part in the chain rule is recognizing when it applies, okay? That's where students are going to have the most difficulty. All right, I'm going to show you now the chain rule is a very general rule, and you can actually use it in many situations, but there are really two situations that you'll most commonly use the chain rule. So I'm going to show you these. I'm going to show you these situations. Okay, and so if you can kind of remember these two settings for the chain rule, then you'll really have pretty much mastered the chain rule, at least initially. Okay, all right. So whenever you have this situation where you have an expression, right? This can be a complicated expression. So this can be a complicated formula raised to a power, right? So not just x, although x is fine, but if you have a more complicated formula raised to a power, okay, so this has to be a number, then that's a situation where you're going to use the so-called chain rule. And here's what the chain rule says is the derivative of this type formula, where you have an expression raised to a power. It says, look, you're going to use kind of the power rule, right? You're going to bring the exponent down, bring the number down, subtract one from the number, just like in the power rule. But the thing you have to remember is multiply in the derivative of this thing inside the parentheses. At the end of applying the power rule, you have to multiply in the derivative of what's inside the parentheses, okay? So it's just the power rule, but it's just the power rule, okay? With this one extra piece thrown in. Here's the second place where you're often going to use the so-called chain rule. If you have a trig function applied to an expression. So this could be x, but this could be a more complicated formula than just x. Here's what the chain rule says. If you want to differentiate something like this, that is a trig function of a formula, just take the derivative of the trig function, like you would expect, right? So if this is the sine, you take the cosine. If this is the cosine, you take the minus sign, etc. But then you have to remember to multiply in the derivative of what's inside the parentheses. Multiply in the derivative of what's inside the parentheses. Let's quickly look at one really quick example to give you a feel for just really how easy the chain rule is once you recognize that you're going to use it. All right, look at this function, 5 plus 6x squared. I want to find the derivative of 5 plus 6x squared. All right, that's what I'm trying to do. I'm trying to find the derivative. All right, now, here's what you need to recognize. Look, this is an expression, 5 plus 6x, right? There's your expression raised to a power. It's not just x raised to a power, but it's this more complicated formula, 5 plus 6x raised to a power. That is perfect situation for the chain rule, okay? Expression raised to a power. So the chain rule says to find the derivative of this, it's so easy. You just kind of use the power rule. Bring the 2 down, just like you would in the power rule, and subtract 1 from it. So you get 2 times 5 plus 6x to the first power. But then there's this one extra thing you have to remember to do to finish off the chain rule. You have to multiply in the derivative of what's inside the parentheses here, the 5 plus 6x. What is the derivative of 5 plus 6x, though? That's easy. What's the derivative of 5 plus 6x? Quickly, before we run out of time. Just the part inside parentheses. What's the derivative of that? 5 plus 6x. 6. Exactly. So at the end, I'm going to multiply in 6. That's it. That's all there is to it. That is the derivative. So it's 12 times 5 plus 6x. Done. Okay. See, just that fast. All right. So see, that's really just the power rule. It's just kind of a fancier version of the power rule, right? Because you have to remember to multiply in the derivative of this base, the derivative of the 5 plus 6x. Okay, well, when we use the chain rule, a lot of the time, that is what we're going to be doing, an expression raised to a power, just like this one, or possibly a trig function applied to an expression. Well, we don't have time to do an example of that, okay, but we'll see that next time, okay? So we're out of time for today, right? So remember, right now your homework is that long homework on products and quotient rules, right? So that's due on Saturday, so don't forget about that, okay? So that one's lengthy, so if you haven't started working on that one, you should start working on that one pretty quickly, all right? So you can get as much progress as you can by Saturday. Okay, and we'll finish talking about the chain rule on Tuesday, all right, with the rest of our examples. Okay, I'm going to stop the recording, but if y'all have any questions,